Hello everyone, my name is Luana and I will talk about the paper A Supervised Approach for Corrective Maintenance Using Spectral Features from Industrial Sounds. The other co-authors of this paper are Matteo Sammarco, Marcin Detyniecki from AXA, and Miguel Campista from UFRJ. To contextualize the problem addressed, let's talk about the main concepts of the industrial revolutions. In the first one, the central element was mechanization. In the second, electricity and mass production were at the core of industrial modernization. In the third, the production automation. And finally, in the fourth and current revolution, we have cyber physical systems. Cyber-physical systems are composed of both computational and physical elements. Industry 4.0 is enabled by digital technologies. Among them, we can mention the Industrial Internet of Things, artificial intelligence, and smart sensors. The centerpiece of the 40th Industrial Revolution is smart factories, where artificial intelligence-based solutions can monitor industrial processes and equipment. In this way, it is possible to dynamically adjust production and create a sustainable system. By adopting AI-based solutions to monitor the industrial plant, decision-making for corrective and preventive maintenance becomes more effective. In our proposal, spectral features of the sound were selected for anomaly detection. The main objective was to improve the classification task using supervised learning and to reduce the model complexity by comparing it with the baseline work proposed by Purohit et al. The proposal of Purohit et al. Contains 5 hiding layers with 64 neurons in the first two and last two and 8 in the central layer. Our neural network proposed has only 3 hidden layers with 64, 32, and 16 neurons. Experiments were performed on the DCASE 2020 dataset, and the performance was evaluated using Fe1 Score and AUC ROC metrics. The DCASE 2020 detection and classification of acoustic scenes and events was a challenge with 6 tasks. In task 2, the goal was to detect anomalous sounds to monitor industrial machines through unsupervised learning. We adopted the proposed dataset for this task and the work of Purohit et al. For comparison. In this specific task, the best results were obtained by Giri et al. With a deep residual network for image recognition, since the authors converted the sound samples into null spectrograms that can be treated as images. While artificial intelligence refers to the techniques that enable machines to reproduce human behavior, machine learning techniques are a subset that adopt statistical methods to enable machines to improve their results through experience. We selected 4 supervised machine learning algorithms for machine status classification. The algorithms selected were naive-Bayes, a probabilistic classifier that assumes that features are conditionally independent; random forest, where the class choice is decided by a majority vote of the decision trees; SVMs, where the classes are separated by hyperplanes; and MLP, a class of neural networks where neurons are fully connected to neurons in the next layer. The evaluation of the results is carried out in 3 steps. In the first step, the Fe1 Score Metric is adopted. This metric combines the recall and precision metrics. Recall describes the ratio of true positives to the sum of true positives and false negatives. This metric can point to situations where the system did not alarm when it should have alarmed. The precision metric is the ratio of true positives and the sum of true positives and false positives. This metric can describe false alarm situations. With F1 score, we try to find a balance between both. In the best scenario case, F1 score is equal to 1. In the second step, we study the impact of spectral features on the AUC ROC metric, which will be adopted in the final evaluation. To do this, we separate the two best algorithms and train the models with the metrics in an incremental fashion. We start with only one of the features and we add a new one at each training and test step. Finally, the AUC ROC metric was adopted. This metric contains the value of the area under the ROC curve that shows the relationship between true positive rate and false positive rate. In this last step, it was possible to compare the results of the proposal with those obtained by Puruhit et al. The first step in our proposal is to manipulate the original audios. The malfunctioning industrial machine investigation and inspection dataset was adopted in this proposed system. The dataset contains samples of four different types of equipment: fans, pumps, valves, and slide rails. Each type has sound samples from four machines represented by the colored circles. Each sound sample has a duration of 10 seconds, and the original sound is mixed with factory noise to generate three SNRs. In this way, the sound samples are presented at SNRs 6, 0, and minus 6 dBs. The lower the SNR, higher is the factory noise. In other words, the lower is SNRs, the more difficult the classification. The next step was extract the spectral features using Python library librosa. Talking about the selected spectral features, the chroma represents the energy of the spectrum into the 12 musical pitch classes. The zero crossing rate, the number of times an audio signal waveform crosses the zero. The Mel's frequency spectral coefficients are coefficients that can describe phonetically the instantaneous amplitude of an oscillating signal. The spectral centroid is the magnitude of the spectral center of mass. We selected also spectral bandwidth. And lastly, the spectral roll-off is the frequency which 85% of the spectral magnitude is below. Then we have six selected spectral features: chroma, spectral centroid, zero crossing rate, spectral bandwidth, null frequency spectral coefficients, and spectral roll-off. The converted dataset is divided into training, validation, and testing. The training set contains 49% of the samples from the original set, the validation set 21, and the test set 40%. The models are trained for 10 separate rounds to average the metrics for each machine type. The oversampling process is performed on the training and validation sets to handle the unbalanced amount of normal and abnormal samples. Data transformation comprises the process of standardizing the samples. In this way, it is possible to compare the different features. In addition, the labels are converted to binary values. The abnormal state class is considered the class of interest and is converted to 1, while the normal class takes on the value 0. The SVM algorithm is represented by the purple bars, NLP by the yellow bars, RF by the pink bars, and NB by the green bars. Comparing the Fe1 score obtained by each algorithm at the highest SNR, the SVM archives the highest values on almost all devices. For the valves, the best result is obtained by MLP. The low value obtained for valves is explained by their low accuracy. In this type of equipment, there is a high rate of false alarm. The same trend is found for other SNR values. SVM archives the best results on almost all devices, but MLP is the better choice for valves. We selected SVM and MLP for this second step, starting with the evaluation of the contribution of the features in the AUC metric. The best results can be archived with all spectral features. Valves have been shown to need special attention for their low Fe1 score value. By adopting all features, we were able to get closer to 1. This behavior is found for MLP and for SVM. In the last step, when evaluating the results for the two algorithms selected in the previous step, we compared them with the baseline work using the AUC ROC metric. Purohit's work is based on dense autoencoder network and uses MEL spectrograms as input. The work was made available in a repository on GitHub, and the model was trained and tested in 10 independent rounds for performance evaluation. For this comparison, the MLP network adopted in conjunction with the spectral features archives the best results on all machines. MLP continues to archive the best results for the other SNRs. Despite not archiving better results than MLP, SVM in conjunction with spectral features also improves the results obtained by the baseline work. Conclusion: supervised learning can address the problem of fault recognition for corrective maintenance. Selected spectral features positively impacted audio analysis. SVM and MLP can improve the baseline work by keeping a lower number of model parameters. For the future work, we plan to reproduce the same workflow for other different critical scenarios. Thank you.